Hello, everybody. So we are still talking about the equations that we use to calculate or estimate the diffusion coefficient in the gas phase, and we are going to discuss another equation. This equation can be used almost at the same conditions that the Hirschfelder's equation can be used for. So it can be used for nonpolar binary gas systems, but this can be used only at low pressures. And this equation is recommended to be used in case of having or having components that we don't know the Lennard-Jones parameters for, the sigma and the epsilon over k, and consequently the omega d. So if we cannot find these Lennard-Jones parameters, we can go for the equation that is produced by Fuller, Schittler, and Giddings. And this equation is very similar to the Hirschfelder's equation. You'd see that it is constant multiplied by t. This is t power 1.75. In the other in Hirschfelder's equation, it was only 1.5. It's also inversely proportional to the sum of the molecular weights and inversely proportional to the pressure. But instead of having omega d and sigma, we have these v. The equation is produces diffusivity in centimeter square per second, T in Kelvin, P in atmosphere, and V is called the diffusion volume. And the diffusion volume is a parameter that is dependent on the types of materials or the types of species that are included in the process of diffusion. So there are some known values that are available for simple molecules which are commonly used. We have here hydrogen, helium, air, oxygen, N2O, carbon dioxide, and so on. In case you have another species or another molecule that is not listed here, you can calculate or predict the diffusion volume from this table, from what's called the atomic and structure diffusion volume increment. So let's say, so we have here carbon, hydrogen, oxygen, nitrogen, chlorine. So these are just elements. So if you have, let's say, methane, so it's CH4. So CH4, we have the volume, the atomic diffusion volume for carbon, and that for hydrogen. So you multiply or add the carbon with 4 times the hydrogen. So it's going to be the diffusion volume of CH4. The same can be done for anything else. If you have straight chain, it's gonna be okay. But if you have a cyclic chain, or a cyclic structure, like a benzene ring or anything else, you have to reduce because the cyclic structure will have lower volume than the straight chain structure. So that's why you have to deduct this negative 20.2 for aromatic ring or heterocyclic ring. So this is how we can calculate the atomic volume. So this is why we have the sigma v, which is the summation of the atomic and diffusion volume increments. If you know it already from here, then you don't have to do any sigma. It's going to be already calculated. And it's very straightforward, very simple. Once you get the diffusion volumes, you can calculate the diffusion coefficient, since all other parameters in the equation are already well known. So if we apply the same or this equation to the same case or the same example that we solved before with the Hirschfelder's equation, we will find that for carbon dioxide and air, we already know the diffusion volume, so it will be just direct substitution in the equation. The temperature 293, the pressure is 1 atmosphere, and we know the molecular weight, so it's gonna give 0.1519. The value that was already there, let me check it, which was in the the value in the table, the actual value is 0.1549, so it's giving pretty much close results to what we got before. So this is another alternative for the Hirschfelder's equation, and this is how we can use it. The next equation is going to be used for polar components. So this is something that is totally different. It's a totally different system because the interaction between the molecules is going to be much more than the interaction between the molecules in case of nonpolar molecules. And this is something that I would like to draw your attention to, which is that the description of the behavior of molecules or gas molecules in case of the non-polar components, is close to the ideal case. The ideal case assumes that the molecules are far away from each other, there are no interactions, there are no bonds between the molecules, and that's why it's very simple to describe mathematically, and that's why the simplest case, or a very famous example, is the simplest equation of state, which is the ideal gas law, which is only PV equals nRT. So this is a very, very simple and straightforward. If you go for non-ideal equations, you find it's getting more and more complicated, because the behavior of the system is complicated and it requires complicated equations to describe this complicated behavior. And the same here. This is what we will notice here, that the equation is getting more and more complicated. In this case, we are using the same Hirschfelder's equation, but the Broco, this person suggested some tweaks to the equation so that it can be suitable for the non-polar or for polar components. And these tweaks are related to the calculation of omega d, the calculation of epsilon over k, and the calculation of sigma. This is why, or this is because the components are very non-ideal, and that's why the equations would be complicated. Again, I would like you to always relate to the complexity of the system and not be just dealing with the equations as just equations that we use to calculate diffusion coefficient. It has to be telling you something inside that this is how things go. The system is complex, and that's why the equations must be complex to represent this complex system. So we will start first by the equation that we use to calculate the epsilon over k. Let's start with this. So we know that this is the dimensionless temperature, which is k kappa T over epsilon, and this is something that's not new. And we know that epsilon AB equals epsilon A multiplied epsilon B under the root. But epsilon A and epsilon B, previously we were able to get them from tables. But in this case, we are calculating the epsilon over, or values of epsilon over k for A and B from this equation, which is a function of TB, which is the normal boiling point in Kelvin, and the delta. Delta is a parameter that we calculate. So again, this is the same thing, but it's getting more longer and more time consuming. So you have to calculate a parameter from another parameter. So to calculate epsilon over k, you have to calculate, or to know what is delta, and to calculate delta you have to use this equation, which is again a function of the boiling temperature, or normal boiling point, the liquid molar volume of the compound at its boiling point, which is not like a difficult thing to find. And then this is mu, which is the dipole moment. The dipole moment is a parameter that describes the charge, the partial charge in the molecules, and how the ability of the molecule to form partial charges, like the partial positive and partial negative bonds in or charges in the hydrogen or water molecule that produce the hydrogen bond. So if you know the dipole moment, you know the VB and TB, then you can calculate delta, and from delta you can calculate epsilon over K. From this equation, from epsilon over K, you can get the epsilon AB over K, and then over kappa, and then you can calculate the dimensionless temperature, which we use to calculate the omega D. Previously in Hirschfelder's equation, we got the omega D from the dimensionless temperature from the chart or from the table, but here you would use this equation, which is a function of delta, which we have already by the way, this is delta for A or delta for B, and then you calculate delta AB from the geometric mean, which is the square root of the multiplication of A and B, of delta A and delta B. And from delta AB you can calculate this term, which is used to calculate the omega D. And to get omega D, you have to calculate omega D node, and this omega D node is another parameter that you calculate from this very complex equation. It is a function of A, B, C, D, E, F, G, H, and they are all function of T star. So if you know T star, and you know these parameters, they are already known parameters. It's not something that you're gonna calculate. So A, B, C, D, E, F, G, and H are already known values. So you substitute with these values in the equation, and the dimensionless temperature will be used to calculate the value of omega d node. If you know omega d node and you know delta, then you can calculate, and of course the T star, you can calculate omega d, and the equation is almost done except for the sigma. So we had values of sigma A and sigma B, which we used to get the average to calculate sigma AB, which is calculated from this equation. So this is another equation that we used to calculate sigma AB. It was 1/2 for sigma multiplied by sigma A plus sigma B. Here it is the geometric mean. And sigma is calculated from this equation as well, which is also a function of the molar volume and the delta. So it's more time consuming. It's kind of more lengthy procedure to follow. But this has to tell you something, that the polar molecules and the non-ideal systems are very hard to describe, and that's why the equations are getting more and more complex. So all the equations that we have described till now are used to calculate the binary or estimate the binary diffusion coefficient. But in many cases, we don't have only two components. We have a component that is, or a species that is diffusing through 4 or 5 different species. So in this case, we have to deal with it in another way, and this is how we can, or what we are gonna discuss in the next video, inshallah. So I'll see you then.